Okay, hello everyone. Today we're going to talk about the center of mass. It's a fascinating topic, and yeah. So let's get to it. It's the final webinar this calendar year. So next webinar is going to be in January, the 3rd, I believe, 3rd of January. So I'll share my screen, and let's get to it. Last week's webinar on YouTube. Yes, I want to do that. There was a lot of technical issues, so I want to cut them out first before publishing it. So sorry about that. I will eventually do that. It just takes. It's very slow to edit video on YouTube. So yeah, it's excruciatingly slow. Anyways, let's talk about center of mass. So center of mass is well, I don't know, it should be something intuitive. You take an object, and a center of mass is where you can balance it. So I've got a piece of toy track. I'll just unblur my background. I've got a piece of track, and if I put my finger at the center of mass, it should balance. If I put my finger here, oh, it doesn't balance. So yeah, it's a point where stuff gets balanced, right? In a way, if you attach something to it, that changes the position of the center of mass. So if you attach a pen, for example, the new center of mass would be somewhere here. So you can balance it like this. Okay, so this is center of mass. In fact, where do you think the center of mass is? Like, I can actually take a picture of myself. Where do you think the center of mass would be in this example? Center of mass of the track and pen. So somewhere below the track. Yeah, that's very good. That's very good. This is a picture of me, and the center of mass must be somewhere beneath, somewhere here. So center of mass. Center of mass. So center of mass has interesting properties, and I will talk about these properties. Not like in the A-level course, we don't talk about center of mass nearly as much as we should, as one should, because it's an absolutely fascinating topic. So let's start with easy stuff. Find the position of the center of mass. Now there's a formula. There's a formula for the center of mass. So the center of mass, the position vector of the center of mass is mass 1 R1 plus M2 R2 plus etc. Sorry, you know what? I should clarify what this means, because I'm just saying random stuff. Okay, so you have point objects with mass M1, M2, M3, and M4. You want to find the center of mass of the four. Let's say this is the origin. This is the point O. Then the vector drawn from O to M1 That's vector, let's call it vector R1, vector drawn from to M2, M3, and M4. So this is R2, R3, R4. So M1, M4, their masses, and R1, R2, R4, they are position vectors. So the position vector of the center of mass, R center of mass, position vector of center of mass. So my guess would be that the center of mass is somewhere here. Well, we don't know M1, M2, and M3, but I mean, if they are roughly the same, the center of mass would be roughly here. And this would be the position vector of the center of mass. So this is the center of mass, and this is the position vector of the center of mass. So the position vector of the center of mass is equal to M1 R1 plus M2 R2 plus M3 R3 plus M4 R4, and divided by M1 plus M2 plus M3 plus M4. So this is the formula. There's a brief version. The position vector of the center of mass is the sum of mass I R I divided by the sum of Mi. And of course, yeah, or sum of, obviously, I starts from 1 to n, I equals 1 to n. It's a brief version of the same thing. And of course, okay, so yeah, don't worry about that. So yeah, this is the definition of the center of mass. Do you understand this definition on a scale of 0 to 10, please? Does everyone understand what a position vector is? Is there anyone who doesn't understand what a position vector is? You don't need to say. Okay. All right. I'll say a few words. Some people. I'll say a few words. So let's say you have a system of coordinates. So what is a position vector? Is a position vector. Let's say you have coordinates x and y, and you have a point somewhere here. Let's say this point is 1, 2, 3, 4, 12, 8. 12, 8. So it's 12 on the x, 8 on the y. But the position vector is a vector drawn from the origin to your current position. So this is your position vector. And the coordinate of this vector is going to be 12, 8, of course. So R. So R is the position vector of point P. So if you're standing at point P, your position vector is 12, 8. It's quite straightforward. It's a bit, how to say it? It's It's a bit weird to call it a position vector, but basically a position vector is a vector drawn from the origin of coordinates to your current position. That's it. Does that make sense? Two. Okay. All right. Good. Happy going forward. And this formula, if you disregard, because you remember that the radius vector contains the x coordinate and the y coordinate. So if you only take the x coordinates of the vector r, meters, yes, it would be the units would be meters. If you only take the x component of vector r, because vector r has x, y, z components, and if you're in 3 dimensions, x, y, and if you're 2 dimensions. But if you only take the one component, then it becomes like this: x, the center of mass, is equal to m1 x1 plus m2 x2 plus m3 x3 plus m4 x4 divided by m1 plus m2 plus m3 plus m4. This is the formula. And the same for y. If you replace x with y, it's the same formula. Okay, so you've got the center of mass. And it's from now on, it's incredibly straightforward. Sounds like I said the word straightforward too many times today. Anyways, we're going to choose where the origin is. It doesn't matter where we put it, but it would be a reasonable thing to put it here. So let's say that the origin, point O, is here. That means this is M1, this is M2, this is M3, and the coordinates, the position of the first mass, x1 is 0, x2 is 3 meters, and x3 is 8 meters. Does that make sense? And from then on, you just use the formula. The center of mass is m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3, and that gives you m1 plus m2 m3, so that's 12, and m1 x1, so m1, so that's 8 multiplied by 0 plus 3 multiplied by 3 plus 8 multiplied by 1. Oh, 1 multiplied by 8. Oh, no. Yeah, 1 multiplied by 8. So that's 9 plus 8. Oh, that's 9 plus 8. That's 17. That's 17 of 12 out of over 12. So it's approximately 1.12. 1.42. 1.42 meters. So it's somewhere here. So somewhere here, if you place, so that's 3 meters, 1.42 somewhere here. So if you place a pivot at this point, the system would balance. Well, of course, there's no rigid rod, but if there was a light rigid rod connecting them, this is where it would balance. It has to be light, because if it's not light, it would the piece of rod on the right hand side would overcome the overcome the math. Anyways, another definition of the center of mass is that another definition of the center of mass, the gravitational force produces zero moment around the center of mass. Gravitational force produces zero moment about the center of mass. When we say about the center of mass, if the pivot is at the center of mass, if pivot is about the center of mass. I hope that makes sense. So if you place the pivot at the center of mass, gravitational force will produce zero moment. Okay. When you have two dimensions, it's just becomes 2 times more work, but it doesn't become harder. Now you have x and y. Let's do it in vectors now. Okay. So I'm going to find the origin, and let's say the origin is here. It makes perfect sense. Well, we did say that the origin is here. So M1 is 8 kilograms, M2 is 3 kilograms, and M3 is 1 kilogram. The radius vector to the first mass, radius vector, R1 is, somebody tell me what R1 is? What is the position vector of mass M1? Zero minus 3, well done. What is the position vector of the second mass? 0, 0. And the position vector of the third mass is 5, 0. Okay. So you don't have to do it in vector form. You can do the x and y separately, but I want to do it for the fun of it. Sorry, that was actually wrong. Should have corrected me. The y-axis is up because we used minus. So this is y and this is x. So you could do x center of mass and then m1 x1 plus blah 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 1 plus and then y center of mass would be m1 y1 plus etc plus divided m1 plus etc. But I'm going to do it as a vector. So the position vector of the center of mass is m1 r1 plus m2 r2 plus m3 r3 over m1 plus m2 plus m3 vectors, and that is equal to m1, that's 8 kilograms, multiplied by 0 minus 3, plus m2, which is 3, multiplied by 0, 0, plus 1 kilogram multiplied by 5, 0, over m1, 8 plus 3 plus 1, so it's still 12, So it's 12, 8 times, so 0 minus 24 plus 0, 0 plus 5, 0. So that's 524 minus 24 divided by 12. 5 over 12, that's 0.42, 0.42, and minus 0. Oh, minus 2. Minus 2. All right, so we can find this point. So this point is somewhere here. So 0.42, so somewhere here. And minus 2, which is here. So we can, this is the center of mass. Center of mass. And the radius vector of the center of mass is this. So radius center of mass. Where is that formula from? Well, we show it in the assignment. It's the definition. I mean, the formula is the definition. So it's not. Yeah, thank you. There exists a point which we call the center of mass, and is defined like that. And it has interesting properties, and we prove the properties, but not you can't prove the definition, because the definition is the definition. So properties of the center of mass. Well, properties of the center of mass is that well, one of them I've already mentioned. There's no moment about the gravitational force produces. So weight has 0 moment about center of mass. The object center center of mass moves center of mass moves center of mass. You can think that you can say that all weight no, okay, sorry, not the center of mass. Center of mass moves like a point object. What does that mean? Well, let's have a look. Let's have a look at this video. So this is a tennis racket being thrown across the classroom, and I press play, and you can see how the racket moves. The center of mass of the racket is approximately at this white point, roughly. Right. So now look at the track, follow the track by focus on the end of the handle. The end of the handle moves in a very peculiar way. However, if you focus on the center of mass, if you look at the center of mass of the racket, this is the path followed by the center of mass. Okay, so let's take a snapshot of that. Right, so the center of mass follows a trajectory that it would follow by a point object. Okay, so if you have, for example, if he was throwing, I don't know, a firework that exploded halfway. Let's say, so you have projectile launched. The projectile would follow this path. And then let's say it exploded halfway. Somewhere here it exploded, and different pieces would fly in different directions. Different pieces of different debris fly in different directions. So let's take gray. So this one would go like this. This one would go like this. This one would go like this. This one would fly like this. This one would fly like this, and this one would fly like this. Like a, yeah, like a firework. But the center of mass at any given moment in time, the center of mass would carry on center of mass of the system would carry on in the original path. So the gray is the individual paths, of debris, but the purple is the path of center of mass. Path of center of mass. And I think this is fascinating. I don't know how about you, but I find this incredible. You don't know, you have no idea where each particle is. You have no idea how many particles are, but you can definitely say that if you know where the center of mass is, because you can do the calculations with the original object. And this is quite cool. Center of mass is, well, the center of mass follows the original path. Okay. And this allows you, so let's say there were only two objects and there's a problem in the assignment where you have some sort of firework which explodes into two pieces. And if you know where one of them lands, you know exactly where the other one should land. Okay. If you think about it, because let's say they break down into two identical pieces. Let's say you have a firework which breaks into two identical pieces somewhere here. And one goes this way, the other one goes this way. And they fly like this. And you know that this one lands here. You know that you found this one. And So imagine you have a firework, it shoots up, it breaks into two identical pieces, or it breaks into two pieces, as long as you know that it breaks into two pieces. One piece flies to point A. Because you know where the center of mass is, you know exactly where to find B. So it's like, yeah. I mean, I don't know. I'm sitting here and I'm smiling because I just realized this. And I was just thinking of a lot of experiments people do where they need to shoot stuff up and then they can't find it. And it turns out if you know exactly that there were two pieces, if you found one, you can calculate where the other one is. This is cool. Anyways, no, the center of mass behaves in the same way as a point mass would, and we will see that in one of the next questions. Okay. Consequence. Well, the biggest consequence here that if there are no external forces, the center of mass cannot move. And this is I would say this is a profound consequence, which, yeah, it's sort of Newton's third law as well. It includes Newton's third law inside it. Imagine you are inside a car, a small light car. If you cannot make it move by pushing it from the inside, because that's not an internal force. That's an internal force. No matter how hard you push on the walls of the car, you won't make it roll. You need to walk outside and push it from the outside, and in this case, the friction from the road, that is the external force. Or there has to be an external force. The external force, when a car moves, the external force is the friction from the road. The friction from the road causes the car to move forward. But if you're inside, you cannot make it move. So you always need to push against something, right? So this center of mass cannot move. And let's look at an example. A person on a boat. So a person on a boat first. So let's say you have a boat and it's in the water and you are standing here. You have a boat, you have a mass, the boat has mass, and you can assume that the center of mass is somewhere here. This is the center of mass. If you walk to the other end of the boat, your feet will push the boat back and the boat will push you forward. And therefore, if you were to walk to the other end of the boat would move. The boat would move and you would be here now. I don't know why you would be underwater, but you would be here. But the center of mass would not move. Center of mass. So if you walk from one end of the boat to the other end of the boat, the boat would shift, you would shift, the center of mass would stay where it is. And because if you know the mass of you and the mass of the boat, you can calculate how far the boat moves, actually. And it actually moves, well, it's the same moment. It's the principle of conservation of momentum as well. There's a lot of stuff going on. So the boat moves because of the friction between you and the boat. Boat moves because of the friction between your feet and the boat. And you move because of the friction. So for the boat, that's an external force. But if you take the boat plus you, that's an internal force. For the boat plus you system, it is an internal force. So to move, you need either a sail. In this way, the wind is the external force, while the air pressure is the external force, or you need a propeller. In this case, the water pressure is your external force. The water pressure on the propeller that pushes the boat forward. That would be an external force. But with no external forces, you cannot make the center of mass change position. A second example is less obvious, but hopefully just as beautiful. A rocket and fuel. So imagine you're in deep space and you have a rocket. And if you know anything about rockets, 99% of a rocket is fuel, typically. Rockets are essentially big fuel tanks with a tiny human attached or a tiny satellite attached. So you have a rocket and there's some fuel inside. Well, when I say some fuel, it's mostly fuel. This is the rocket. And the center of mass is here. If the rocket spits out the fuel, at a really high speed. So the rocket is now somewhere here. I don't know. A million light years away. Okay, million kilometers more likely. Rocket. And the fuel is, because it spits out the fuel is far back. It's spread, of course. It's more spread out because you don't use it all at the same time. That would be silly. That would be a catapult, not a rocket. But roughly, this is the fuel. And if you find the center of mass, it would be here. because the pressure produced by the rocket engines is an internal force for the rocket plus fuel system. The center of mass cannot change. The center of mass cannot change. So if you think about it, when the Apollo astronauts landed on the moon, the center of mass of the astronauts, the rocket, and the astronaut was still at the launch pad. If you shoot a rocket into space, the center of mass is where you started. Okay, which is quite cool. I mean, of course, there's other things to consider. There's like the gravity of the Earth, gravity of the sun, etc., etc., etc. But I mean, in a simplified version of this, it's still there. But the thing is, it's not important for us where the fuel is. It's more important for us where the rocket is. So that's why it's makes sense. Okay, and third, there was a proposition of a rocket that could fly without a fuel, without any fuel, and it was sort of a distant, well, a very close relative of a perpetuum mobile, which is a what's it called? What's a perpetuum mobile? What's the translation? Ah, anyone help? Someone help me. Free energy, perpetuum mobile. It's the engine. What's it called? Perpetual motion. Yeah, perpetual motion. So basically, this was a model of a spaceship, and it had a hollow tube on the outside, and they said you take a pump, and it pumps water through the outer shell of the rocket. The water goes here, and because it is following a curved path, there's a centrifugal force. There's a centrifugal force acting on the water. So centrifugal force from the water. And well, you know centrifugal force. When you're in a car and you make a sharp left turn, it feels like you're being thrown out to the right. And this is a force, and there's a force here, centrifugal force, which acts on the outer shell of the rocket. Force. And because it follows a straight path here, because the water follows a straight path here, there's no centrifugal force here. No centrifugal force. And the rocket should propel itself upwards. So who can tell me where's a problem with that design? Why is this design faulty? Using the ideas center of mass. Well, no, I mean, look, there is a force, and this force should push the rocket and the water up. um, Centrifugal force, well, it's not fictitious. I mean, obviously you feel it. It's there. But it obviously would. If there's a force that pushes the rocket up, the rocket would move. So if the rocket would move, the center of mass would move. It is internal. Yeah, it's an internal force. There's something wrong with this design. We definitely know there's something wrong with it because that's an internal force. That's an internal force. Or force. And whenever somebody tells you that you will use an internal force, which is centrifugal force, that's an internal force, which will propel something forward, you say, no, that's not possible. There must be something wrong with it, right? So how the water is kept moving is there's a pump here, but that's not important. Once you get the water moving, it can, if there's little friction, it can keep moving on forever. That's the thing, yeah. The problem is that actually what hasn't been considered is the water follows a curved path here around the corner, and it follows the curved path around the corner here. That means there's a outward force here, and there's an outward force here, and these three forces are balanced, so it can't move. Okay, so it looks like a beautiful design, but no, it's not. So this is a rocket with no fuel. It doesn't work. Okay, because there's centrifugal force here as well at the corners, which will push the rocket back. And I will talk about centrifugal force a lot in year 13. For now, just please never use the word centrifugal force in school. You won't get into trouble. And please never write it on an exam paper. The examiner would be really mad at you. No matter what you do, don't use the word centrifugal in school. You can ask your physics teacher why you shouldn't. I'm sure you will hear some excellent answers, and I will agree with every single one of them. Yeah, centrifugal force is just too complicated. That's why it is covered in second year of university typically, and of course at COMPOS. But yeah, it's a tad too complicated to explain it properly, so people tend to confuse it with centrifugal force. Sorry, centripetal force, and that's why teachers usually get mad when you try to use centrifugal force. That's the gist. Anyways, problem 5. Two identical small masses held 2 meters above the table are held by a compressed spring and a short strain. The rope is cut and the masses move in opposite directions. The lower mass hits the table 0.3 seconds later. Find the position of the center of the second mass when this happens. So, interestingly, they're giving us a spring. They're not telling us the spring constant. They're not telling us how much energy is stored in the spring. And effectively, they're asking you to calculate the gravitational potential energy of the second mass, right? Because if you think about from the point of view of energy, there is elastic potential energy here plus gravitational potential energy. Now, when this one falls, it will hit the ground. So it has no gravitational potential energy, but it still has kinetic energy. And the other ball would move up, and it will have gravitational potential energy plus kinetic energy. You don't know this. You don't know this. You don't know this. But somehow they're asking you to calculate gravitational potential energy. Like, what? That doesn't make any sense. But now you know stuff that you didn't know before. You know stuff about the center of mass. You know that the center of mass doesn't move without internal forces. But gravity is an external force, so the center of mass does move, but it moves in a predictable fashion because the only force acting is the gravity. The only force acting is the weight, or is gravity. Gravity. The center of mass follows moves like a point object dropped with zero velocity, zero initial velocity. So yeah, the first mass moves down here, and then the second mass moves up, so it moves somewhere here. So in 0.3 seconds, the center of mass falls by so S is equal to ut plus 1/2 gt squared, which is 0 plus 5t squared, which is 5 multiplied by 0.3 squared, which is 5 times 0.09, which is 0.45 meters. Okay, so the center of mass used to be at 2 meters, and now it is at 1.55 meters. 55 meters. So that means center of mass is 1.55 meters above ground. So if the first mass is on the ground, at the ground level, and hit the ground, so it's 0 height, so the second mass must be, first mass is 0 meters above ground. So 0.3 seconds later. And so the second mass must be, because they are identical, second mass is 3.1 meters above ground. That's it. It's quite cool, isn't it? Like a problem that seemed incredibly difficult turns out to be very benign when you consider the movement of the center of mass. Right? Type 1 if you think it's cool. Oh, the silence. That's embarrassing. Okay. Okay, so once again, we know that the center of mass had to move a little, moves as if it was dropped. So it has to fall 0.45 meters, because that's what any object falls in the first 0.3 seconds. In 0.3 seconds, anything, like my calculator, if you calculate 0.3 seconds, it hits the ground. Or you can actually use it to measure time, right? If you take a ruler, 45 centimeters, if you need 0.3 seconds, That's how long it takes to fall 45 centimeters. Is 0.3 seconds. So you can use it. You can time things with that. You can measure time. And then yeah, if you know where the first mass is, you automatically know where the second one is, even if you have no understanding of the properties of the spring. You don't know what type of rope it was. You don't know anything, and yet you are able to calculate things. So yeah, that's quite cool. I wanted to talk about. I wanted to talk more about the movement of center of mass, but let's do this calculation. I know it's one of the examples. Find the center of mass of the laminate. So basically, it's a flat disc. It's a flat disc made of metal, let's say, and it has a hole in it. And you know that the radius of the big circle is r. The radius of the big circle is r. And the radius of the small circle is half r. So how do you find the center of mass? Well, you can think of it as, what if there was another hole in it? Right. So if you see, what if there was another hole in it? Holes would look like this. Plus, imagine you have, oh, sorry, radius of the small circle. As typo. So the big circle is r, the radius of the small circle is r/2. So you can think of this disk, this uneven disk, as being made up of two disks. A disk with two holes in it, okay, plus a small piece like this, a small disk, right? So if you put the small disk into the big one, you get the original one. We have something that is called the area density. Area density. We usually call it sigma. What is it? Well, area density is the mass of 1 square meter, which is a mass of 1 meter squared of the sheet of metal. That, yeah, of the sheet. Okay, the area density. So the mass is area multiplied by sigma. That's some of the things that we're going to use. So the mass of this one, so we call it M1, and we call this M2. M1 is going to be the area, which is pi r squared minus 2 small ones, 2 pi r/2 squared, and multiplied by sigma. Do you understand? Does everyone understand how I got this formula? On a scale of 0 to 10, please. Let's see how. To 10. 19. Nice. Nice. Okay. All right. So you understand anything less than 10? I would like to know, please. Okay. So you're happy with that. So M2 is the area, which is pi r over 2 squared multiplied by sigma. So it's quite straightforward. So I'm going to simplify this. So M2, or should I? Yeah, I should. It's pi r squared minus um that's a good question. Surface S. My initial guess would be that S stands for surface. That's why is usually S in physics. S is area. And sigma is the Greek version of S. So it's kind of yeah, like mass and mass per unit length. This is area and area per unit length. That would be my initial guess why it is, but I don't know the answer to your question, why it is sigma. Pi r squared minus 2, I'm simplifying M1, pi r squared minus 2 pi r over 4, so it's pi r squared over 2 sigma. So M1 is pi r squared over 2 sigma. Okay, so it's half. It's half of the original. It's half of the big disk. Interesting. So M2 is pi r squared over 4 sigma. Okay, so M1 is obviously 2 times bigger than M2. You can see it from here. And then you choose an axis. And you choose where it's a good color. There's no good colors here. So you could choose the x-axis. So this is 0 on the x-axis. And so the big disk is at 0, 0. And the small disk is at a point which is half r, half r. So the big disk, the big piece with 2 holes in it, is at position 0 meters. And the small disk, x2, is at position 1/2 r. Yeah, 1/2 r. This is the coordinate. And now from here, we can work out the center of mass. X center of mass is going to be m1 x1 plus m2 x2 divided by m1 plus m2. Now you need, so m1 is pi r squared over 2 sigma plus multiplied by x1 multiplied by 0 plus m2, which is pi r squared over 4 sigma multiplied by x2, so 1/2 r, divided by m1 plus m2, which is pi r squared over 2 sigma plus pi r squared over 4 sigma. And therefore, so this is 0, so this is pi
r cubed sigma pi r cubed sigma over 8. And this is 3 pi r squared sigma over 4. So pi cancels, r cancels, sigma cancels, and this cancels, this becomes 2. So it looks like it's going to be r over 6. Ah, that's beautiful. The center of mass is at point r over 6. So it's somewhere here, which makes perfect sense. This is half r, so it's here. This is the center of mass. Okay. I think that's a bit tough doing this one. I'll I'll walk you through how to do this. Maybe perhaps I won't do the whole thing, but hopefully to get an understanding. So you have a triangular sheet of metal or whatever, triangular sheet of something. And here it is. You want to find the center of mass. You want to find the center of mass. So you can think of it as, well, this is the x-axis. I'm going to cut it. I'm going to cut it into slices like this. And for each slice, I'm going to find the center, which is going to be the x coordinate, x1, x2, x3, x4, etc. And I'm going to find the mass. And it's going to be m1, m2, m3. So m is the mass of the slot of this strip. m1, m2, m3 is the masses of the strips. And x1, x2, x3 is the position of the strips. Now, what is the shape of each strip? I mean, it's a simple question. Trapezium, thank you. It is a trapezium. But if you take if the strip is very narrow, you can assume it's a rectangle. It's very close to a rectangle if you take a narrow for narrow strips, it's approximately rectangles. Okay, so you can think of the triangular sheet being made of strips, of rectangular strips. It shouldn't affect your calculations too much. Yes, you can absolutely integrate for the true area. But finding the area is not a big deal. It's for finding the center of mass. Okay, right. So what are we on about? Well, we need to find the for each strip, we want to find the mass and the position. So let's take a random strip. Let's call it strip number I. Strip number I. Strip number I. Number I. And the mass of that strip, well, we need, it's a rectangle, right? So it's a rectangle. And the height of this rectangle is y. So the length of this rectangle is 2y. 2y is the length of this rectangle. The width is delta x, delta xi. So area is equal to 2y I multiplied by delta x I. And the mass is this multiplied by sigma. So that's where we get the expression for the mass. This is the mass of this whole thing. No, the mass of this strip. And the position of the strip is xi. So what do we have? Because this is 0, this is 0, and this is y, this is y, and this is another y. So overall, that's 2i, 2y. But I really hope that you see that this problem is exactly the same as this one, as the problem 1, which we were doing. Problem 1. We had 3 masses, and all we did, we found the mass and the x. The mass and the x, and we need to use this formula to find the center of mass. Now the problem here is just you have many more masses, so you need a short way of adding them. So mass of each strip, mass of strip is delta mi is equal to 2yi multiplied by sigma multiplied by delta xi. Yes, perfect. Position of strip is xi. Very straightforward. So what we need is we have the center of mass is equal to the sum of the xi multiplied by delta mi over the sum of delta mi. Okay. It's approximately. Sorry, it's approximately. Because it's an approximation, of course. Now, I will substitute delta mi with this, and it becomes sum of xi multiplied by 2yi sigma delta xi over sum of delta mi. But this y, of course, depends on x. If you think about it, the equation for y, this line has equation y equals 2 minus x over 4. That's the equation of this line. You can verify that the gradient is minus a quarter, the y-intercept is 2. So this line has equation this. Okay. Therefore, instead of y, I'm going to use sigma xi 2 multiplied by 2 minus a quarter x I sigma delta xi sum of delta mi. Oh, sorry, sum of delta mi, that's the same thing. I need to substitute that as well. It's going to be the sum of 2y, which is 2 minus a quarter xi, sigma delta xi. Now this looks scary, but we've of course have a trick up our sleeve. So x center of mass, what we need to do is to make the width of the strips progressively narrower. We need to make them infinitely narrow, in fact. Making strips infinitely narrow. And if we make them infinitely narrow, we get closer and closer to the true area. Because as the narrower the narrower the strips are, the closer we are to a true triangle. Yeah, I hope you can see that. And that means x center of mass is equal to the limit as delta x I tends to 0 of this expression. I don't know if you hate me by now, but hopefully some of you would be able to say "whoa" in a few minutes. Raghav, yes, of course. We can find the area of the triangle as 1/2 BH, of course. But that's not the point. That's not the point I'm trying to make. The limit of this expression, it's a property of it's called a Riemann sum. This is a Riemann sum, and when delta x tends to 0, delta x becomes dx. Delta x becomes dx. And sigma becomes integral. And xi becomes x. So this is equal to the integral of x multiplied by 2 minus a quarter x sigma dx. Integral of 2 multiplied by 2 minus a quarter x sigma dx. Would you look at that? Of course, we need the limits, and the limits is from 0 to 8 because that's the x values from 0 to 8, 0 to 8, 0 to 8. So it's the integral 0 to 8 of, and now you just simplify that. Sigma is a constant, so sigma goes in front. So this is 4x minus x squared over 2 dx divided by sigma integral 0 to 8 of 4 minus x over 2 dx. Sigma cancels, and we are left with something, well, I'd say quite extraordinary. 0 to 8, so we integrate 4x, so that's 4x squared over 2 minus x cubed over 6 between limits 0 and 8. And 4x minus x squared over 4, 0 to 8. And we just substitute 8. So it's 4 multiplied by 8 squared over 2 minus 8 cubed over 6. I wonder if I messed up somewhere. 32 minus 64 over 4. 32 minus 64 over 4, that's what? 32 over 216. 32 minus 16, 16. So the area of the triangle should be 16. Let's check. It's half base times height. Base is 4. Height is 8. Half base times height is in fact 16. So, okay, at least the bottom one is not messed up. So that's 2 times 64 is 128 minus, whoa, 8 cubed. So that's going to be 8 squared multiplied by 4 multiplied by 2. 2 cancels 3. 8 squared, 64 times 4, 128, 256. 156 over 3. 128 times 3. 300 and... Okay, sorry. That's the end of my brain for today. So 3 times 128 minus 256, 128. It's 128 over 3 times 16. 128 over 16. That should be 8. 6 times 8. Yeah, 8. 128 over 16. 8 over 3. 8 over 3. Isn't that beautiful? 8 thirds meters. Whoa, so that's quite cool. We found it. Of course, you know the definition of these. By definition, the center of mass of a triangle is 2/3. It's 1/3 of the way. So it's 2/3 of the way from the vertex to the base. So quite cool. But it works for any triangle. Any triangle, the center of mass is 2/3. So if you have a triangle on its side, and this is 0 and this is 9, the center of mass is going to be 3. This is by definition. It's 1/3. If you draw a line from the median line of the triangle from a vertex to the midpoint, 2/3 of the way down is the center of mass. We know this very well. It is the centroid, of course, for a triangle. So yeah, but what we did is we had this complicated thing and we ended up with very simple integrals. I know we haven't done integrals yet, but some of you have in school, I guess. Some of you've learned integration, but the other assignment, the maths assignment, is on integration. So enjoy. Right. So I hope you've enjoyed that. I hope that was useful. I hope you've learned something new today. I wish you all a Merry Christmas and a Happy New Year, and I will see you on the 3rd of January. So no webinar next week. And yeah, have lovely holidays. All right. All right. Yes, thank you. Assignment 3 or assignment 4? I'll give you a link. Right. So okay. They should be open. Can you please check that you can open them? Yeah. Okay. So there they are. Sorry. We need to publish them in the group. I'll do that now. All right. See you, everyone.